The first speaker of the morning session is Sebastian Franco from the City College of the City University of New York. And he's going to talk to us about 40 crystals for Toric Calabi-Yau 4-folds. The exploration continues. Please go ahead, Seba.
Okay, so thank you. So once again, thank you, Rak and Masahito, for organizing this workshop. It's very nice so far. This is a workshop. We are more or less interested in similar things. So what I will try to talk today about is intended to be a little bit more fun. So I will talk about things that hopefully people find interesting. And probably I will be a little bit brief given the amount of time that we have. And if you want to discuss afterwards, I'm happy to do it. So I'm going to talk about 4D crystals and some new things that crystals for 4-dimensional Toric Calabi-Yau 4-folds, and some of the things that I have been doing recently. It's work in progress. Here, this is a nice picture. What you see here is the brain brick model, or the covering space of the brain brick model for C4. For the brain brick models, we developed the analogs of perfect matchings. And what you see here is the canonical perfect matching that will correspond to the empty room configuration for C4. Okay, so this is the analog of the usual picture that I will probably show you in the next slide. Okay, so this is an introduction. So, this is the workshop BPS and crystal melting and things like that. So the BPS spectrum of difference on Toric Calabi-Yau 3-folds is captured by a statistical model of crystal melting that was introduced by Aguri and Yamasaki in a very nice paper long ago. And the crystalline structure that underlines that model is that of the brain tiling for the underlying geometry, or equivalently the dual periodic quiver. They wrote it very nicely in that paper. And you have seen pictures that look like this. Imagine that you have C3, you have the hexagonal lattice that will correspond to the brain tiling for that. In red, I put some edges that correspond to this canonical perfect matching. And then you start flipping or moving or changing some of parts of the perfect matching, and you get these images that when you look at them with some imagination, or you do a rhombus tiling of this thing, they look like stacking three-dimensional boxes in a corner. Okay. So today I want to talk about some crystals for Calabi-Yau 4-folds. And why do I want to talk about what is going to be the context? Well, it's partly related to what I already discussed yesterday. So there will be like 2, perhaps 3 slides that are going to be repeated. So do we have something that is analogous to this brain tilings, but for Toric Calabi-Yau 4-folds? Yes, we do. We developed them with Rak and Sangmin some time ago. It was the result of a program that we had, that we wanted to understand the 2-dimensional 0,2 theories generically living on D1 brains probing Toric Calabi-Yau 4-folds. And what we wanted to do is we wanted to develop something or a brain configuration which had the same features of the brain tilings, meaning that it really simplifies the connection between geometry and quantum field theory. It captures the entire infinite class of theories and so on. This is what we call the brain brick models. Some other motivation, at least for me, that has already appeared in other talks is, the ideas of Nekrasov, or Nekrasov and Piazzalunga, or the Magnificent Four model, in which they want to compute a refined index for D0 brains and D8 and anti-D8 brains on C4. And the variables are solid partitions, meaning 4-dimensional boxes, so 4-dimensional Young diagrams. Okay, so there's already some hint that you want some kind of 4-dimensional crystal. And what I'm going to do today is I will explore the crystal melting model for Toric Calabi-Yau 4-folds that are based on brain brick models. I introduced this in this paper, and then there was a very nice paper by Jakan, Masahito, and Rak a few months later that get these things from the point of view of the Witten index, and more things. So this is a slide that I had yesterday, so I will go quickly over that. What I told you is that the kind of theories that are engineered when you have a Toric Calabi-Yau fourfold on D1 branes are two-dimensional 0.2 theories with some additional structure. That additional structure is what allows us to treat them what endows them with some nice combinatorial properties, which underlies the entire brain brick models. And one of the things that I mentioned is that there's some toric structure of the J and E terms, in a sense that every Fermi participates in two J and two E gauge invariant interactions. If you want to make them look like kind of a superpotential, right? So I gave you this example yesterday. This is the toric diagram for the cone over Q111, which is very nice geometry. Is U1 vibration over S2 times S2 times S2. You can imagine that this is one or two natural generalizations of T11 or the conifold for Calabi-Yau fourfolds. There's another one, which is a natural generalization in another sense. Here is the quiver for that. I'm representing Fermis with red lines. Chiral fields by arrows. It has 4 gauge groups in this case. It has 6 Fermis. And here I give you a list of the J and E terms. I told you that if you give me this geometry, you have to provide me these 2 pieces of information for the gauge theory. And these 2 pieces of information determines that you're coming from this geometry. And you cannot just give me the quiver and ask me, what are the J and E terms, because even satisfying consistency conditions for 2-dimensional 0.2 theories, I wouldn't be able to nail down these things. These things are determined by many equivalent reasons. One obvious effective field theoretic kind of way of thinking about this is that the geometry determines the global symmetries of all these fields, and as a result, it determines what you can write as J and E terms. Okay, and I told you that this structure can be nicely captured by a picture, which is a new version of the quiver, which is what I call the periodic quiver. Okay. Again, this is one of the 3 slides that are going to be repeated. So the periodic quiver was a quiver that lived on a 3-dimensional torus. The 3-dimensional torus nicely captures U1 cube out of the U1 fourth isometry of the Toric Calabi-Yau fourfold. It has the J and E terms built in here. We can read them from the minimal plaquettes, or conversely, or more precisely, from the dual edges. So the edges in the dual graph, which is a brain brick model. Yeah, so that's an underlying search. So what is a brain model? It's a type 2A brain configuration, which is T dual to a D1 brains over Toric Calabi-Yau fourfold. Yesterday I motivated it as some natural step. Well, it's not so natural, but it's a natural step in the evolution of Hanani-Witten setups, if you want. It's the next step in the evolution. They look like this, right? So what happens is that you have D4 brains which are wrapping 5 directions, 0 and 1, which are going to be common to another type of brain in which the gauge theory is going to live. And then it has, in this notation, it also spans 2, 4, and 6. And then the next 5 brain is going to span 0 and 1, and then it's going to be wrapped over some complex surface, meaning something that has 4 real dimensions in 2, 3, 4, 5, 6, and 7. So these 2 dimensions are the dimensions in which the gauge theory lives. For me, 2, 4, and 6 are going to be such that they live on a torus. And the whole configuration is point-like on the 8-9 plane. So you have rotational symmetry there that corresponds to the U1R symmetry of the gauge theory. And what I'm going to do is I'm going to combine 2, 3, 4, 5, and 6, 7 into 3 complex variables such that 2, 4, and 6, let's say, are the arguments of x, y, and z, and then they live in a torus. So the entire non-trivial part of the story is in sigma, and sigma, what I told you yesterday, is something that you obtain from the zero locus of the Newton polynomial. So someone gives me the toric diagram for this Calabi-Yau fourfold. I have a polynomial with some complex coefficients. I can absorb 4 of them, but this determines something, and that is what I will call the brain brick model. Now I will interchangeably use the brain brick model word for this thing or for some skeleton or tropical limit of this configuration. Any questions so far? Okay, and this generically is a configuration that reduces the amount of supersymmetry in the right way because, you know, the NS5 brane wrapped on sigma behaves like 3 different types of NS5 branes perpendicular to each other. So it breaks 1/8 of the supersymmetry, and the D4 branes break the other half. Of course, you can have non-generic configurations which have higher supersymmetry. Can have 8,8, 4,4, 2,2, might be 0,4, things like that. Okay. Okay, and most of the non-trivial structure that I want to discuss is captured by some tropical limit or some skeleton of this sigma. Well, the projection on T3, you have to visualize it in some way. I told you that sigma is given by a polynomial in 3 complex variables equals to 0. So, you know, one way of representing it is by what we call the coamoeba projection, which is a projection on T3. And that is what we normally call the brain brick model. And I told you that it's the dual of the periodic quiver. So it contains the same amount of information, right? So this is, you know, this truncated octahedra is the building blocks that you get for C4 or for orbitals of C4. It's the analog of the hexagonal lattice for Calabi-Yau for 3-dimensional Calabi-Yau threefolds for C3. In fact, it's, you know, you can do it for any dimension, and for Cn, it's, you know, some n-dimensional permutahedron. And so we told you that you know, we have to think about these surfaces as representing the skeleton of the NS5 brane. Inside each of these bricks, you have different branes that each of them corresponds to one of the nodes in the quiver, or one of the gauge groups in the quiver. Then the entire structure represents the NS5 brane. And when I read it in the gauge theory, you know, these bricks corresponds to gauge groups. One type of phase corresponds to chiral fields. The other ones that I represent in red corresponds to the Fermi fields. And the edges correspond to a J or E-term plaquette that couples the corresponding Fermi to all the chirals that terminate on it. Not any random. Of course, the things that you obtain from string theory construction are well behaved. But if you thought that, okay, these are your building blocks, you cannot go and build anything you want. There's some basic properties that you have to satisfy that ensure that you satisfy all the consistency conditions of the 2-dimensional 0,2 theories in a nice way. So that you can build them in some basic properties of these things, but I won't go into it. Okay. So as I said, these things simplify the connection between geometry and gauge theory. And I said that you only appreciate this after suffering through it. And here I summarize the same dictionary that I just described for you. Very good. And that is the last thing that is going to be repeated is that I want to talk about, yeah, I'm not sure how to move that thing because I don't see it in my, yeah, this is about triality. I told you it's an infrared equivalence for 2-dimensional 0,2 theories, not 2-dimensional 0,2 theories that come from this kind of class of theories is general. that was found by Gadegukov and Putrov yesterday. Since it was a more general talk, I went quickly over it, but let me just be a little more detailed here. So this is a cool representation of what you call the simplest kind of theory that we can look at, which is two-dimensional super QCD. Why we call it super QCD? First of all, it has single gauge group. These nodes that you can call it frozen nodes or framing nodes are global symmetries. We call it QCD because we have one type of, or N1, N2, so we have three types of flavors of fundamental or anti-fundamental matter. You have Fermis, you have incoming chirals, or fundamental chirals, or anti-fundamental chirals. So these are the three things that you can have. Of course, you can split these nodes if you want. In this case, there's no other reason for splitting them. And then, just to make the picture more symmetric, we added that Fermi connecting nodes 1 and 2. This is just to make the three pictures look the same. Of course, we could have lived without adding this thing, and then it would appear, something like that would appear eventually. One of the things that you see is that the rank of the gauge group is constrained by N1, N2, and N3, because in two-dimensional 0,2 theories, the gauginos contribute to the anomalies, so you cannot have anything here. So either fix N1, N2, and N3, and then the number of colors is fixed, for example. By the way, since it's allowed by symmetries, here there's a cubic coupling between this Fermi and these two chirals. Right? So the dual of this theory, or the triality dual, is this other theory. And I said that it looks similar in spirit to cyber duality for the following reasons. First of all, you change the number of colors. In this case, the number of colors has to change because now the flavors change their identity, so they change how they contribute to the anomaly, so it has to change in order to cancel the anomaly. You can check that the way it changes is that it's equal to the number of incoming flavors minus the original NC, which is very similar. It's identical to cyber duality also. The electric flavors turn into some magnetic flavors, which are things that transform differently under the global symmetry, which is the same thing here, but instead of having two types of them, we have three types of them. And then in cyber duality, you would add some fields that we call mesons because are singlets of the gauge symmetry, which are, from the point of view of the electric theory or the original theory, look like composites. And we do the same here. So, what we do is we generate the mesons that are obtained by combining incoming chirals with other fields. So here you have incoming chiral and Fermi, it gives you this Fermi. Then you have an incoming chiral and outgoing chiral would produce a chiral meson here, but that chiral meson would participate, which was originally you have a cubic coupling here. Now it becomes a quadratic coupling with that between this new chiral field and this Fermi. We are interested in low energy theory, so we integrate it out because it's massive. Now these two fields are massive. That's why they're not here. Otherwise, we would have to add those fields. And then we do this thing again, using this as a starting point, and you apply the same rules to obtain the other theory. And there are three theories that if you have only one gauge group and you apply duality, triality on the same node, are closed under triality. I will call this thing triality. I will call this going just in this direction, inverse triality. I know it's a new quiver mutation of order 3. And in this context will be related to the non-uniqueness of the two-dimensional 0,2 theories that come from the Calabi-Yau fourfold. I explained yesterday, even from the mirror symmetry point of view, how this duality is captured. And I also told you that in the class of brain-brick models, if you want to, triality is very general, but if you want to consider the trialities that relate brain-brick models to theories that are also described by brain-brick models, what you have is some kind of a local operation whose simplest representative is the cube. And it just corresponds to doing this replacement somewhere in the brain brick model. Okay. Questions so far? There. So what is this crystal melting model for Calabi-Yau 4 force? I'm going to be very brief. There's a lot of nice physics that we can discuss about this. Here it's going to be just basic 2 slides about it. So let me give you the example of C4. Here I have the covering space of the quiver for C4. It's the dual of this truncated octahedron. Remember, the gauge theory for C4 is the dimensional reduction of to 2 dimensions of n equals to 4 super Young Mills. It's a theory that you have seen already in at least 3 talks. It's a theory with 3 adjoint Fermis and 4 adjoint chirals, which are literally the dimensional reduction of the 3 chiral fields in 4 dimensions of n equals to 4 super Young Mills and the vector multiplet in 4 dimensions of n equals to 4 super Young Mills. It has some J and E terms. And since there is only one gauge group in this quiver, I will say that this crystal or this periodic quiver has only one type of atom, which corresponds to this single type of node. More generally, there will be more than one. I will sometimes be interested in this space, which is the universal cover of the periodic quiver. And I will call this 3-dimensional quiver space. It has some coordinates x, y, and z of the periodic quiver. I will also consider in this talk like general Toric Calabi-Yau 4 force, which is, if you give me another Calabi-Yau 4 force, you have to consider the corresponding periodic quiver. It's a problem that we already solved over many years by working on the brain brick models. And on top of that, I will consider general flavor configurations, or general framing flavor configurations, either because they're coming from some specific brains that you want to consider. You heard a lot about, if this is the D0 brain theory, you heard a lot about D4, D6, and so on. Very interested in D8 also. But more generally, it's the problem I want to consider. I want to consider general flavors. So I will have, NQ incoming chirals. So additional flavors, I mean fundamental field transforming the fundamental representation of some of the gauge groups. I will have NQ tilde outgoing chirals, and I will have M psi Fermis. These are flavors. I will call them Q tilde, some size. And generically, they will have couplings that were not discussed so far in the talks, but there were questions in the previous talks about these things that look generically like this. Well, so there will be things that have an incoming chiral field and an outgoing, and a Fermi flavor coupled to this OAIJ that just means some field, some operator made out of chiral fields in the original quiver, or in the 0-0 theory, or in the 0-0 part of the spectrum, if you want. So some OIJ, maybe just one chiral field, maybe a number of chiral fields. If you are considering specific D-branes, these things literally tell you what the embedding of that D-brane is, because by looking at what happens with that operator, you see when those flavors become massive. So for example, if they can become massive, you see what it means to separate the branes. Then you have other couplings that look like that. Again, one Fermi flavor, one chiral flavor at some chiral operator in the gauge theory. Then you have more general things where you have 2 chiral flavors coupled to some Fermi operator in the quiver, which might be the product of chirals and one Fermi. It doesn't have to be a Fermi, fundamental Fermi in the original quiver. It might be a product of things. And then you have the same thing. One is the J terms, and the other one is an E term. So this is the general setup that I want to consider, and I will give you examples of how these things look like and what do they mean for the crystal. Okay, so these are chiral and Fermi operators made of fields in the original quiver. Original means unflavored for me. And you have seen this this quiver, for example, in Noshita stock. That corresponds to the, call it N and bar here, to the D8 and the anti-D8 break here. Yeah.
General knowledge of given Toric Calabi-Yau for generic configuration of brains, which favoring gives by the D6 or D.
Well, I would say a few things. So the way I say, if you give me a D6, it's like, when you do D3, D7, so all the three, all these kind of things, you can see here, well, in this case would be trivial, for example, whether you couple to X, Y, Z, or W, right? Because, they will tell you that, let's say, your brain is trapping certain space, that when you give an expectation value, if you're allowed to do that, gives massive to this thing. So you can read where how things are going to be separated. There are other properties that I'm going to mention, which have to do with the relation between these numbers, right? So you know that in this case, you have just one chiral, you have more chiral, common chirals and other things. You know that in other examples, you have, say, the dimension reduction of the chiral field, which is the chiral Fermi, and then you have things which are dimension reduction of the hyper, that will influence these things.
Yes, it's very serious for I'm going to say the difference of what I'm favoring like if I have a D brain for the 4 versus 6 or D4 or something.
Sorry?
Like for example, if I take a D6 on a divisor or a D4 on
Yes.
4 things, I would have a different type of favoring.
I will have different types of labels, yes.
Yeah, is it clear which brains give which kind of favoring?
Yes,
Some
yes.
are chiral,
For me, all the ones that you say are basically just chirals, chiral Fermi, or pairs of chiral Fermi, just the dimension reduction of the hyper. It was lower than. Yeah, it's a simple fact. So, what is the crystal before melting? It's, they have atoms in which are molten. Look, I'm not a native speaker, and I guess that there are so very few native speakers in this room, so I don't know if the word molten exists, but not melt. The molten crystal, every atom there, atom or stone, some people call it, is in one-to-one correspondence with an oriented path of chiral fields in the periodic quiver, which starts from a chiral flavor Qi. Okay, incoming chiral flavor Qi. Modulo the J vanishing of J and E terms relations. Vanishing of J and E terms. Okay. So the crystal is actually going to be 4-dimensional. There will going to be an extra dimension on top of this 3-dimensional quiver space. So the 4-dimensional crystal corresponds to atoms that are on top of the periodic quiver. That extra dimension allows you to distinguish operators that differ by what we call, by closed loops. There's one basic type of closed loop, which is the analog of a superpotential, things differing by a superpotential term for Calabi-Yau threefolds, which is what I call chiral cycles, which is what you obtain when you multiply one of the terms in the J terms and one of the terms in the E terms for a given Fermi. When you multiply the chiral fields for those two things, you get a closed loop. You get 4 of them for every Fermi. And you have to make those atoms be different. So one natural way to distinguish, to provide this extra dimension is by using some R charge assignment. I want to distinguish things that are on the same place of the periodic quiver, but because I reached that operator and then I added a closed loop, but I added more fields, so it has to be somewhere else. Seeing 4-dimensional things is difficult, so one of the things that you can do is you can slice these crystals, or either a molten or molten, at different values of the depth or at different values of the R charge, and every slice is some kind of 3-dimensional, looks 3-dimensional. So here you have a picture for the crystal for that quiver that we had before. before melting, okay? So you have one atom at the tip, then you have 4 atoms, and I'm not drawing all the arrows in the periodic quiver, then you have more and more. Here I'm not using our charge, I'm just counting the number of chiral fields. You know, the chiral cycles for the C4 theory are of order 4. So already here you have one of the atoms at 0,0, which is overlapping, it's the first overlapping atom with that one. Again, it's just, you know, if you want to explore this thing a little bit, that's how you will look at the crystal. So crystals can be infinite and finite, and I'm going to just say very basic things, which are these are related. Part of this thing is related to what Cyril was asking. So depending on the relation, I'm going to be very basic about these things. You know, depending on the relation of the number of incoming chirals, flavors, the outgoing chiral flavors, and the Fermi flavors, you can have different situations, right? You can have infinite crystals. You can have infinite but effectively lower dimensional crystals, you know, the things that you will have if you have a D6 brane or something like that, in which, yes, it's infinite, but there's one dimension that is not being explored by the crystal, or you can have finite crystals. This is what happens, again, at this basic level, if you have more flavor Fermis than incoming chirals, because you have, again, heuristically, more relations than places to start from. And I will give you an example of that. Yeah.
Any term of the distance is like finite with the spectrums or
I guess, yes. At this point, I just want to I just want to play with this, and I will explain to you why I want to play with this. Okay. So I will today I will look at the finite, not because they're especially more interesting for that, but because they're useful for the kind of things that I want to do.
Is there another other finite in the tree for this?
Yeah, yes, of course. Yeah. And simplest example, conifer. You know, you have fundamental and anti-fundamental flavors. Whether you frame, whether you start your pass, and you have, let's imagine you have n and n plus 1, something like that. Whether you use the ones that you have n or whether you have the ones that n plus 1, and then you have all these Nagao, word crossing, and then you reach the PT and the DT, reach ideally it's something. Okay, so I want to do the final. Okay, and you don't see any of the titles, I don't see the letters either, but okay, those crystals can be molten, can be melted. I know this is a user story. I would call I mu a crystal configuration, which is either molten or not. All the atoms that are surviving, omega mu is what I removed from the atom. Sometimes I call it the melting configuration, but I'm not sure that's what I should call it, the melting configuration. There's a chiral path algebra or path algebra of chiral fields that are all open-oriented chiral paths in the unflavored quiver. Then you can mod out by the ideal of vanishing J and eta relations. And the melting rule is going to be something like this. Right. So if you have some operator, which I will factor as some operators and some other operator that goes from I to another node J in the remove atoms for some operator in this algebra, then the operator that doesn't contain this other thing has also had to be removed. So this is a usual story that to remove an atom in the crystal, you have to remove all the ones that are above it, and being above it is determined by having a chiral field connecting them. That's it. Very good. So molten crystals corresponds to ideals of the algebra and so on. So one of the things that I will write is this kind of let's call it partition function that will contain information about the crystal melting, which is a sum over all these configurations, where you have one variable for each of the nodes, the types of nodes that you have in the quiver, and it's going to be raised to the power of the number of atoms of that type that you have in that melting configuration. Okay? So those are the kind of things that I will build today. So I said that I want to build, today I want to study those crystals and with a focus on the finite crystals because they're interesting, but this is my real, this is really killing me, this thing. This is my real motivation. My real motivation is slightly different. Now, might be cool, might be misguided, but this is my motivation. And it's the following thing. There's something very interesting, which is cluster algebras, that Fomin and Selevitsky introduced the same year that Cyber introduced cyber duality for us. So, it's an important year in which this idea came from the heavens to people. And it's everywhere or in many places in mathematics and physics. And for a simple person like me that comes from physics, I guess that the reason why they are everywhere is because they capture some universal structure that appears in many places. So they appear in algebraic geometry, like the Grassmannian. They appear if you think about triangulations of surfaces. They appear in scattering amplitudes more recently, integral systems, Susy gauge theories, the crystals for Calabi-Yau threefolds, and so on. Okay. So there's something universal about these things, and that's why it's so interesting, because it's an idea that applies in many places. That, to me, is why they are interesting. And it has some ingredients, and I'm going to listen for you. I'm not an expert in cluster algebra, so my notation might be different from the usual one. So you have some matrix Bij, which is basically defining for you a quiver. In subsequent work, they added what they call potential, which for us is going to be a superpotential. So that's an ordinary quiver, the type of quiver that we think about when we talk about 4 dimensions with superpotential. So we know those things. It has coefficients, one for each node in your quiver. Then they have other things which are called clusters, which is, again, one for each node in the quiver. Right? And then there are transformations of these things. Yes. Well, I don't know, I'm just meaning something that defines a quiver. Right? So, something that can be the adjacency matrix of the group.
So it's like the full adjacency matrix of the
yeah, I know.
Anti-symmetric.
We should know when I tell you how to transform, but let me just, it's just a quiver. I won't even use it. I won't even use it. So, how it was, under a mutation on a node K, right? It transforms in this way, which is literally a quiver mutation for us. And if you had a potential, it transforms exactly as you would transform a superpotential in cyber duality. Then the coefficients transform in this way. The coefficient of the dualized node gets inverted, and other coefficients pick contributions depending on whether there is proportional to a dualized node for every arrow that connects it by an incoming chiral field or an incoming arrow into the dualized node, right? Again, this is something that is very rings a bell for all of us physicists, because we have seen very similar things before. And there is a transformation of the clusters that looks like this, right? You have a product of all the clusters that are incoming, the product plus the transformation of the clusters that are in the outgoing arrows. You might include the coefficients if you want. If you don't want, you can set them to 1. And then you divide by the CK at the step before. Now, I would call these cluster transformations, but these look like many things that appear in many contexts, like Plucker relations. It looks like a lot of things that appear in all these contexts. Okay, very good. So to me, all these parts are very natural. They're very similar to many things that we know and love, especially quivers with superpotential, cyber duality. It's very well, all these transformations are very well motivated for us. So the question is, now I gave you some other new class of very well motivated from physics kind of quivers. You can think about them as generalized quivers, but it's the two-dimensional 0,2 types of quivers. These kind of quivers come with a very well motivated from the physics mutation, which is the one that corresponds to triality. And on top of that, they come with a very well motivated class of combinatorial objects, which are these plane brick models. So I would say that it's probably natural or reasonable to hope or to expect that there's a generalization of cluster algebras that is really well motivated from physics, right? It's not right now. People consider all kinds of generalizations of cluster algebra. I think that this one should be there. And as I said, the fact that it's underlying, they have all these nice objects underlying them, or connected to this type of quivers is nice. So my question is, can we find such a generalization, and do I need to see some system like this one? Hopefully, ideally in the future, many, but can I see at least one system to which these things apply such that it can guide my search? And what I will do is I will look at this, I will look at this, well, in that case, the Toric Calabi-Yau 3 crystals were a nice place where all these ideas play a role. And that's why I will look at the Calabi-Yau 4 crystals to see if I can get some hints about how to get these things, right? So I would say that this part of the story, we have it because we have the quivers now, and we have how to transform under triality, including with superpotential or J and E terms. I will give you evidence of, well, I will assume this, and I will tell you that that's something very nice for us. So I would say that that part is also fine. And then I will argue that these partition functions for the Calabi-Yau 4 crystals is probably related, or the thing that we should consider there. Very good. We will see how far we go, right? This part we don't have, of course, sadly. Okay. So to do so, I will start the second part of this stage of the talk, which is an empirical, experimental part of the talk, where I want to build the data to draw those conclusions. And this will force me to think a little bit about these crystals. So the example I will consider is Q111, which I mentioned yesterday. We first found it also with Dongbook, and then we considered it more with Rak also. So let me show you again the quiver for D1 brainstorming the cone over Q111. That is the only thing that I know how to consider, but it's one that is nice, and that's why I would like to do a few things there. I already told you what the quiver is. I already gave you the toric diagram. I already told you what the J and E terms are. And it has a periodic quiver that looks like that, and a brain brick model that looks like this. I mean, this is not the unit cell. This is part of probably more than one piece of the unit cell. This is showing also probably it's clearly showing more than the unit cell, right? Because you have several copies of one and so on. So that's the periodic quiver. So there are many, what I say, brain brick models for this theory, or what we call toric phases, but I will just consider this one. And this is nice because it has a periodic triality cascade. So this is a sequence of trialities that gives you basically the same quiver, right? So you can see it very easily. You start from this quiver, you mutate. We studied this long ago, but you do triality on this node, and you get the same quiver up to a rotation. Then I dualize 2, you get the same quiver up to a rotation. Then you dualize 4, you get the same quiver up to a rotation, and then you can continue doing the same thing again and again and again. Right? Very good. So I want to add flavors to this thing. So I want to construct crystals by adding flavors or framing flavors to this thing, and I will start from a single Fermi flavor, right? And I want to do that because I want to generate finite things, and this is the most obvious and basic configuration in which I have more Fermis than chirals, such as 1 Fermi and 0 chirals. And this property is going to be conserved by the cascade, right? So this will lead to finite crystals. So I can give you the cascade at even steps and odd steps. They look slightly different. They look very similar, but slightly different. This is a framing node. We can think that these extra flavors are connected to some node. We can say it's the same. You see that we have a number of Fermis that remain greater than the number of incoming chirals. And people were asking yesterday, oh, what happens to the J and E terms? Well, you have all the J and E terms that I already gave to you for fields exclusively in the original quiver, but you also have these couplings that I will package in something that looks like a superpotential that couple that involve the flavors. So all these things are Fermi flavors, and the Qs are chiral flavors. So you have 2 types of them. You have some things for some, let's say, intermediate Fermis that are multiplied by 2 sets of chiral fields that involve 2 consecutive chiral fields. And then you have something at the end on each end. And you can set those J and E terms for those Fermi flavors to 0, and this is what they produce. And it has a nice implication for the crystal. What it does is, it tells you that there is some path starting from the first chiral and involving 1 chiral field in the quiver that is set to 0. There's another path using the final chiral field and one of the fields in the quiver, which is set to 0. And then there are relations between paths that start at consecutive chiral flavors. So there are atoms in the quiver, in the crystal, that you can reach in 2 different ways. We call this, the spine of the crystal, because it gives you an interlacing of the framing flavors at the top. And these relations at the end, I will call the top vanishing atoms. Now, it tells me that this operator is not there in the crystal. And they lead to a finite crystal in a way that we are going to see. And there are similar ideas for Calabi-Yau threefolds. This is what I was telling Cyril. Now, Chuang and Schaferis do it for the conifold, for example. And at the odd steps, it looks very similar. It's slightly different. Sorry, by the way, what I did is I rotated all the quiver in such a way that it's given in the same order of the same one, of the original one. Okay, but you see that still it's true that you have more Fermis than chirals and the same kind of structure. So how do you build the crystal? For building the crystal, you have to do this. You have to look at the operators made out of chiral fields, starting from the chiral flavors, modulo J and E terms, and make sure that you efficiently use these vanishing relations at the endpoints. To me, that's very complicated. I don't know how to tell Mathematica in which direction to solve things, which relation to use at the end, because you might have an operator that lives very far from that, in principle, from that vanishing relation that but you can deform it. Maybe you don't reach to deform it, so you have to make it this in an efficient way. And the periodic quiver is a way to do that, right? So so you can translate everything in the periodic quiver to some 4-dimensional vectors where, the 3 first entries are, tells you how these things are connected in the quiver space, or the periodic quiver space, and the last one is some R-charge assignment. Of course, I only care about the topology of these things, but this is an assignment that works well. So the periodic quiver is designed to take care of these relations. And I will talk about 3 types. I will build the atom. Yeah.
So maybe I missed that. When you have the flavoring, others that stay with the rotation.
Sorry?
And does the periodic quiver still? I mean, you still periodic quiver when you have the flavor.
I will build on top of the periodic, and you will see how. And I will now construct for you. I want to construct the final atoms that are in my crystal. I will tell you what the crystal is, but I will go through 2 steps. I will construct something I call the primary atoms, which are, let me construct at any R charge all the possible operators that start from this kind of fields, and then let me kill the ones that involve that relationship using the periodic quiver to guide what I do. So, and then I will subtract these guys from these ones, and these are the atoms in my crystal. Okay, so let me consider the step 6 of the cascade, which corresponds to having 3 atoms at the top. Right, 3 Qs, and there are 4 Fermis, I guess. So, if you look at the operators at the beginning, there are 3 atoms that are equal to 0, which are just the Qs. Now I will set the Qs to have 0, and they're at the top, so that's 3 atoms. Then you can continue. I don't remember which fields you use there, but you have some number of atoms at R charge equals to 1/2, R charge equals to 1, and so on. This is very similar to this picture that I show you for C4. And you can build. I will stop here for a reason, but you can keep building. This is in principle, this is infinite. There's nothing finite here. I didn't use the vanishing relations. Now, what I will do is I will build the vanishing relationships, and I will build all the atoms that start from them, because all these atoms have to be out of the picture, because you can show that any atom that is here, that is in the other construction, you can deform whatever way you generated that atom and make it look like a vanishing relation. So this is very nice. It starts at one more step. Remember that the vanishing atom involves a Q and an X. So in this case, it starts at R equals to 1/2. They start at the endpoints at these 2 special flavors at the end, and then it starts emanating from them as you grow deeper, and they grow and they grow and they grow. Now there's some overlap between these 2, so there's some left over, and at some point the 2 sets become equal, and from that point they grow together. Right? So there's no reason to keep looking for more of them. So here I give you what's left after remove. So this is the crystal in this case. Sliced according to R charge. So in this case, well, I didn't say, okay, in this case has 66 atoms, and you can check that 3 of them have on the same position in X, Y, and Z, and so on. You can say all these things. Very good. I didn't show you here how they're overlapping with each other, but of course it's nice to see how they overlap with each other. That structure can be nicely put in some Hasse diagrams. So let me show you how they look like. So this is step 2, 3, 4, and 5 in the cascade. These are the 4 types of atoms. This is just a representation in 2 dimensions of the crystal, and tells you, there are 2 top atoms, and who is below them, and so on, and so on. Then we are going to apply the melting rule to this thing. And you can continue. It looks very nice. Or I don't know. It looks nice to me. And you can continue. You can grow the crystal if you want by triality. Every time you do the triality, you keep growing the crystal. Here I show you everything until step 10 in the cascade. And there's some nice properties, some patterns that you can figure out. So there's some nice information about what are the number of top atoms, what is the number of atoms there, how many atoms of each type. There seems to be like some piece of the crystal is used by the next layer, and so on. So there's a lot of experimental things to be dug from there. And you can really construct the partition functions. You can use these Hasse diagrams and say, let me go over the melting rule and see what I have. And they're explicit and you can generate them. And they're not particularly illuminating. You have some parts which are basic. You didn't remove anything here in the ones. Then it has a top atom of type 4, one top atom of type 3. This one has 2 atoms at the top of type 4. Then you can look at the last one. The last one gives you all. Okay, the last one gives you all the atoms in the crystal, but more than that, you don't see any. Well, I don't see any relationship between them. And at any order, it tells you, for example, these terms that there are 84 melting configurations with 2 atoms of type 1, 6 atoms of type 2, 10 atoms of type 3, and 17 atoms of type 4 removed. Okay, so this is very nice data that you can generate out of these things. You can do another thing, which is you can just count the melting configuration, right? You can do that just by setting all the y's to 1, or you can determine that independently without the computation of these partition functions, these defined partition functions, and an intermediate set. You can calculate them directly. And this gives you these numbers. Okay. Okay. I would argue that all these partition functions and/or these numbers should be generated by the generalization of the cluster transformation that we want to come up with. So here you see why, I picked the finite crystals. Of course, if I want to deal with the entire thing and see how they relate to each other, I can use the infinite crystals because these things have some information there. And probably, well, I'm not sure I can truncate them very easily. But moreover, when you consider the finite crystals, even when you unrefine, you have finite numbers there. Hopefully, this putative generalization of the cluster transformation that you have also have the nice properties that the usual cluster algebras have, which were surprising in these days, that this Laurent phenomenon, integrality of the coefficients, and positivity of the coefficients. So ideally, if we manage to reproduce these numbers, we are in good track.
How fast it goes? Is that factorial?
I plotted. I don't remember. It goes very quickly, and these first 3 numbers are very easy to come up with. Yeah. So this type of data is what they go very fast, and it grows very fast because of the extra dimensions. I think. So this type of data, for me, plays an important role in informing our search for generalization of cluster transformation. So what is the wish list? The wish list is, can we find the generalized cluster transformations that, if we do that, can we generate these partition functions recursively? Now, this is what we did for Calabi-Yau threefolds, and we reproduced some nice results for people like Benjamin Young that are combinatorists. You don't have to actually do these things. You might be able to generate recursively. I did try. There's some natural guess. Probably there's a way in which you can really know what that cluster transformation is. I think there are a few natural ideas of what this could be. I tried them. They did not work. But even if you're like epsilon away from the right thing, you will get it wrong. So let me put it differently. I don't think that you can have a collection of objects that are defined recursively with these similar combinatorial properties, and there's not going to be a recursive way to find these numbers. Maybe it's not elegant, but I guess it should be. So do I have 5 more minutes? Yes. So the next title is called Stable Variables. So remember that I told you that the coefficients transform like very similar way in ordinary cluster algebras. I will consider that change of variables, where the important thing here will be that I will transform the coefficients of things that are connected to the mutated node by incoming chiral fields in this case. This is very well motivated because it looks like the exponential of the transformation of the fractional brane charges that we use to derive this triality from branes and quadrality in 0 dimensions from branes and so on. So it's a very natural thing to consider. So we consider these things with Coulomb. So this is a very natural thing to consider. So let me show you how they look like here. I will call them X now. So I will call X1, X2, X3, and X4, the initial variables there, and then I will give you the Y given by that expression as a function of the step. Some nice property in this particular quiver, which is not generic, which the products along the diagonal are constant. For example, it's X1, X3, and X4, X2 all the way around. You can write them for general even and odd step. And then you can take these crazy partition functions and write them in terms of these variables. And they show this nice stabilization. Probably this is expected. I don't know. For me, it's nice and it's impressive. This stabilization phenomenon that we observe with Digger also for Calabi-Yau threefolds. And what I mean by stabilization is that now the partition functions written in these terms of these new variables, at every step, they basically contain the steps of the previous, the terms in the previous steps, and you just add in new terms, where previously they look completely different. I think that this is nice evidence that this is a nice change of variables. We proposed this long ago for Calabi-Yau threefolds with Digger. Mathematicians liked it for some reason. This is a student of Greg Musiker. She proved it for the conifold, partially for F0. For them, it's something that is highly non-trivial. The way they call it is this partition functions for the crystal, they call it the F polynomials. And what they say is that they prove that there's a change of basis conjecture by Igor and Franco, which leads to the stabilization of the F polynomials of Fomin and Celebinsky. Okay, so I think that this is evidence that that change of variable is indeed what we want. So it's what covers point 2. So let's go to the conclusions. So we introduced a statistical model of crystal melting for non-compact Toric Calabi-Yau fourfolds. I show you some studies of the crystals that come out of them for general flavors / brain configurations, if you want. I developed some efficient ways of generating and analyzing these crystals. That's not trivial in its own. We studied the behavior of the crystals under triality, focusing in this talk in the case of finite crystals. And the driving, at least for me, idea is I want to come up with some generalization of cluster algebras based on 2-dimensional 0,2 theories and triality. So what do we have so far? The transformation of the quiver and superpotential, we had it from the start. I would say that the coefficients on the transformations, which are the stable variables, we almost had it from the start. It's there, and we have some nice rich data here. We can generate more if you want, but that's enough. I mean, the one that we have already is quite enough. Rich data in terms of these partition functions to try to infer the cluster transformations, or at least to be busy and spend some time on it. And of course, once these ideas, I'm not going to pretend that you have to do it for 1 time, 2 times, 3 times. After you do it a couple of times, probably you can understand what it's in the general case. There are M-graded quivers that correspond to Calabi-Yau M+2 folds that we studied also with Cyril. They have order M+1 dualities, and on top of that, there's something that I introduced with my student Hassan long ago, which is there's an analog of the brane tiles for them that we call them dimers. So probably at that point, it would, if this is successful for Calabi-Yau fourfolds, that's a big if. It would be natural just to do for arbitrary M using the same ideas. Okay, so thank you.
Thank you, Seba, for the very interesting talk. Any questions in the audience? Yes.
Is the partition the equation is then computed like computing the character of the
Sorry?
What was the long thing
Yeah. I'm not sure. I'm not an expert on those things. So I'm not going to say that it's a character. Yeah.
Any other questions? So can you write the generating function for the partition functions? Is there that's like a grand canonical?
Yeah,
partition function?
we did those things for Calabi-Yau 3 force. I guess that you can do these things for here.
Oh, so how did they look like for Calabi-Yau 3 force?
You can look at our own paper with Igor. I mean,
Okay.
you can do this.
Okay. Yeah,
The square partition function relates to variance of Calabi-Yau for
Sorry?
So your partition function is that related to some invariance of Calabi-Yau for
I guess that in some variables it will be. So at this point, this is the game I'm interested in because I think it's the one that was relevant for Calabi-Yau 3 force. But yeah, I think that the answer is yes.